All right, so another quick video about mechanical properties and talking about stress strain. So let's start and see what we can understand about this topic. So what I'm doing here is talking about some mechanical properties of materials and how different materials can have different properties. The two main ideas that we are covering here is stress and strain. These aren't the mechanical properties per se, but these are what influences the properties. So you might have heard about Young's modulus, and that is a very crucial material property. You might have heard about shear modulus of a material, and then similarly you could have a bulk modulus of a material. You could have a Poisson ratio of a material, and all these come under the mechanical properties of materials. And different materials have different features, different properties, but they all follow some sort of pattern. So you can have metals, you can have ceramics, and then you can have polymers and so on, and they all will have sort of similar ish set of these properties, right? So let's take a look at how these properties are governed, what these properties are, and what are we talking. So very crudely speaking, the fundamental definition of stress can just be given as force divided by area, and strain is equal to a relative change in length. And now based on these two definitions, you could have two different types of stresses and strain, right? So you could have one case where you have true stress, true and engineering. All right, so in case of the engineering stress, this is given by the force divided by A naught, or the initial cross-sectional area, and the strain for engineering strain is given by delta L divided by L naught, or you could write this as L final minus initial L naught divided by L naught. So it's a relative change, final minus initial divided by initial. All right. And on the other hand, when you are trying to write true stress, let's write that with white color. True stress is force divided by the instantaneous area, cross-sectional area. So instantaneous cross-sectional area. And then you could have a strain that is given as the ln of L instantaneous divided by L naught. So the formula becomes different. And what I'm referring to the cross-sectional area and the length here is that imagine you have, let's take a rod, for example. You have this rod that you are trying to elongate, and after some elongation it attains this length. So let's draw this out. It has this new cross-sectional area and this yellow color. So this initial length over here in the pink color is L naught, and the initial cross-sectional area, which is over this, is A naught. In the yellow color is the final length, which is this one, which can be given as Li, or the instantaneous. The instant when you're doing the measurement, that is what we're talking about. And that is Li, or length instantaneous. And similarly, you could have a cross-sectional area cross AI instantaneous. Keep in mind the material or the stuff remains constant. So the total amount of stuff remains constant, which means that your total volume will remain constant. So you will have A naught L naught equals to AI Li. So your volume at any instant throughout the elongation process will remain constant. All right, and that is given by this formulation of A naught L naught equals to AI Li. And following that, you could write, as we're discussing, again the true stress as sigma over AI, your true strain as sigma, true strain, my bad. This should be sigma, which is, or sigma true, force over AI, and then epsilon true will be ln of length initial divided by L naught. On the other side, you have your engineering stress, which can again be represented as sigma E, sigma engineering, given by force divided by the initial cross-sectional area. And then similarly, you could have engineering strain be given as epsilon engineering, can be written as delta L over L naught, or basically L I minus L naught over L naught, right? So always keep these two distinct definitions in your mind. And using this definition of stress strain, now you could plot a stress versus strain curve. And in this plot, what is happening is that when you are elongating a material, you are trying to see how it behaves. So you could have, again, just like the previous diagram, you could have something like this, that you let's say a rod, and then you try to elongate it. It sort of becomes longer in length but smaller in cross-section area. When you try to do this, you will obtain a curve looking something like this. And then this curve can look different for different materials. And what I have here, a key thing to keep in mind is that in this pink line that I drew on the plot, this, let's call this the pink line. The pink line is a linear line. Keep in mind the linear line. So it will be in the form of y equals to mx plus c. So it's linear plot. All right. Or to be more precise, you could just even write y equals to mx. It has a slope. And the curves that we are drawing here is simply stress versus strain. Right? And that's what we're trying to draw here. And this is what the linear line is. And the property, if you guys remember, the first property that I wrote at the top that we were talking about, the E, or the capital E, which is also referred as the Young's modulus. Now that capital E is given as sigma over epsilon, or stress divided by strain. So it is simply speaking the slope of the curve. And what curve? You have to be very precise here. It is the pink line. Pink line's slope. So meaning in this range, if I take this triangle, this is some sigma, this is some epsilon. So this slope here is given as the Young's modulus, or capital E, right? So let's look at some example of sort. And over here, let's go back with this value. A few more important points to note down on this plot is at this corner at the top, the highest point, a point over here, and then this point over here. These four, so let's call them 1, 2, 3, 4. Very important labels. 1, 2, 3, 4. Here, the point number 4, which is the final point of this curve, can simply be given as the fracture point or the fracture strength. And the point number 3, which is the highest, is written as the ultimate tensile stress. Right? And then the point number 2 is can be referred as the yield stress. YILD, yield stress. Oh, sorry. Yeah. And then the point number 1 is referred as the proportionality limit. So let's dive a bit deeper into what is happening here. So if you look at this curve, you'll see that when a material starts deforming, you are pulling it apart. It has elastic deformation, which means that it is a non-permanent change. So what will happen here is that this material, this can revert back to its original shape, revert back to its original shape or original size. But at certain point, this material will cross this boundary and then start doing plastic deformation. And once this plastic deformation starts, it's sort of no turning back. It's sort of a do or die situation. The material can just keep going forward, but there is no turning back. And following that, so it's sort of a process. Following once the plastic deformation begins, it will keep deforming plastically. At a certain point, you will hit this phenomena, which is necking, where you'll start noticing these necks in your material. So if it is looking like a rod like this, you'll have these necks which will create cracks in your material, and then eventually it will lead to a fracture, which means sort of breaking. Your material broke apart into two different halves. All right, so let's compare this on the curve. Again, keep in mind this linear elastic area over here is this straight line. I'm gonna highlight it with this blue straight line. And now this blue straight line is referred as the elastic region. So if I extend this forward, this is referred as the elastic region. Meaning that if a material goes up in this direction, you can always bring it back in this direction if you would like. Right? And that's the main point when it comes to elastic deformation. But after that, if you see this curve, that I'll highlight that with a yellow curve. In this part is now, let's use this part over here will be a sum of elastic plus plastic. So some elastic deformation is still happening, but the plastic deformation has started to take place. So you can draw another line over here. Dot, 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 dot. So this is E plus P, elastic plus plastic. And this blue part that I drew, and this is the point that we were talking about being, so let's call it the point 1. This point 1 was your proportionality limit. Proportionality limit. And the point 2 over here will be over here. Let's draw that with a big yellow circle. Right, so this point 2 is your yield stress. Your point 2. Right? Saying that at this point, at the point 2 or after the point 2, your material has yielded and it is a complete plastic deformation. So after point 2, it is all but plastic. So I'll write here only plastic deformation. Your material, and the way to remember that is that your material has yielded. So therefore, after the yield stress point, you will only have plastic deformation. Now, interestingly, in this area, in the till the point you are you are elongating the material, plastic deformation has set in. Till this highest point, the stress that you can apply to this material, this point which is referred as the UTS. Let's write it in red. UTS, or even some darker green maybe. I'll draw this with like a greener line. This is referred as work hardening. And what is happening here is that you are making your material stronger. So the work hardening, or also referred as strain hardening, in some sense you are making material stronger. And we'll soon look into how does material become stronger. But the important thing to note here is this point number 3. I'll circle it with a red dot, which is the UTS, or ultimate tensile strength or ultimate tensile stress. Ultimate tensile stress, which is again this highest point. And after this point, let's use the light blue color. After this point, you have necking. So if I go back to the previous diagram, the necking, so let's write it here. It's getting a bit crowded. So the necking, I should write, starts after UTS, which means that once your material has achieved, or you have provided, or you have acted that ultimate tensile stress on it, after that your material is no more one single entity, but it will start to neck apart, and it'll keep necking till the point where you hit this final blue dot, which is referred as the fracture stress. So this will be your point number 4. This will be point number 3. So here your 4 point is your fracture stress, which means, so fracture is this over here, means breaking. Your material will break apart. It will fail. It will fail. It won't be able to sort of be one single material anymore. So this is a very, very important sort of fundamental diagram of stress strain curve and what we're trying to look for. Let's try to solve a problem and see how we can approach this. So if I give you this problem, you have a cylindrical specimen of brass. I give you the diameter, the initial diameter. I give you the tensile modulus, which is 110 GPa. I give you the Poisson's ratio, and I give you its pull in tension with the force. I give you the force, and I tell you that I'm doing a totally elastic deformation. So it's in the elastic region. I'm asking you what is the strain experienced by the specimen. All right. So let's look at how you can approach this question. All right. Let's try to solve it over here. Or I can just write it here. So a few important things to write down that we have been given here. So you have been given the force acting on your material, which is 40,000 newtons. Right. Problem 3. You have been given the diameter d naught, initial diameter of 20 millimeters, and then you have been given the tensile modulus, which is also the Young's modulus. Let's write that down here so that you know. So tensile modulus, also referred as the Young's modulus, I give you that equal to 110 gigapascals. Pascals is the unit of pressure, and I'm saying this is gigapascals. Then I also give you the Poisson's ratio as 0.35, and then I'm asking you to calculate the strain. What is the strain experienced by material? And another important thing to note is that I give you that we are working in elastic region, meaning that I've only created an elastic deformation in my material. So again, let's try to write down. Remember that strain is given by the expression epsilon, and we know that stress is force divided by area. To be more specific, force divided by A naught. That would be the engineering stress. And then similarly, the engineering strain is given by delta L over L naught. Another way to define engineering strain is through Young's modulus. So we know that Young's modulus, capital E, is equal to stress over strain, right? So I can write the strain equals to stress divided by Young's modulus, capital E, right? So let's try to solve this down. To calculate the stress, you have F divided by A naught. Here F is given as the force, which is 40,000 newtons. So 40,000 newtons divided by pi d naught square by 4. That's what an area of a cross section is. If it's a circular cross section with d naught diameter, you put that in 20 millimeters of d naught, you get 40,000 newtons divided by pi into 20 into 10 to the power minus 3 meters whole square divided by 4. And then you can solve this and you can get some value of stress. So let's say you have some value of stress. All right. You have been given the value of Young's modulus. So you can write that strain is equal to this stress value, whatever you calculated, divided by E. And then I'll just use the blue circle again. So let's say some stress value divided by E is given as 110 gigapascals. You can convert that into 10 to the power 9 pascals, and then all the units will cancel out, and then you'll get some strain value from here. And if you want to check, an answer is given over here. So again, it calculated the A naught pi d naught square by 4. This is the cross-sectional area it got. And then it had the epsilon equals to sigma over capital E. It gave you this expression. And then you can plug in the values. And then this is what you will get at the end. You can check it with your answer. But this is how you can use these formulations and calculate different values. All right. Now, let's come back and try to understand a few important things. Here, this point P in this curve, again, it's another stress strain curve. Very important thing to note here, which I previously mentioned as well, is this point P. I'll write it with pink color over here. This point P on that curve is nothing but the proportionality limit, the point at which you hit your proportionality. And by proportionality, it simply says that y was proportional to x, or stress was linearly proportional to strain. I could write simply sigma equals to E times epsilon, Young's modulus times the strain. And till this point, again, keep in mind, till this point, you only have only elastic, all right? But after this point, till the yield stress, you have, or also rest of this sigma y, which is marked here, sigma y, this is referred as the yield stress or the tensile stress. You could use any word. Let's I think it's on, let's call it the yield stress for now, for this material. Some people refer the tensile stress as the ultimate tensile stress. Let's call this the yield stress for now. All right. So again, important thing, till the proportionality limit, you have only elastic, but after the proportionality limit and till the yield stress, you have elastic plus plastic. And after this yield stress, you have only plastic. All right. So keep this distinction very clear in your mind. Cool. And this is how, again, same idea, your material can look like, it can transform. You have this material, you elongate it, and then after this point you have necking happening, necking, and then after that at the point F you have a fracture. The material fails in engineering terms, right? And this is what referred as, using this same curve, stress strain curve, you can understand ductility and brittle nature of a material. You could understand how different materials behave. So like at let's look at this plot where you have three different materials. You have a ceramic, you have a metal, and you have a polymer. We know that these three materials are very different from each other, right? So where does that difference come from? And if you look at the stress strain diagram for these three materials, you'll clearly see the difference. Let's start with metal. Metal, again, that's general curve that we just saw. You have a tensile stress, a yield stress, an ultimate tensile stress, and a fracture. For polymer, you notice that this value of at which you let's use the red color. This proportionality limit is super far apart, like it's very high in the strain value, which means that polymers are very elastic. You can stretch them. You can stretch them because again, see the strain. Strain is what? The relative change in the length, which is so high for polymer till the yield point, right? This is the yield point. Meaning that you can stretch polymers, you can stretch, for example, rubbers so much. And this is the reason. And they will break apart at a very high strain. So this is the failure for polymers. On the other hand, a complete opposite example, let's look at the ceramics. So this green line that I'm drawing, this is the ceramics. You'll note that the ceramic also or can sustain high stress. So they can take in a lot of stress, but they cannot stretch too much. Cannot stretch too much. Why? Because note how early this breaks. This cross point is the failure point for ceramics. Ceramics will fail so early in their straining process. You see how small this strain is compared to this red line. And that's why ceramics can sustain a lot of force because they can sustain this high of stress, but then they will break very quick in terms of the length, while as polymers can can stretch a lot. Polymers can stretch and sustain all this extension, but they cannot sustain a lot of stress. And this is how you can define, or you can bring up the concept of ductility and brittle nature of a material. A material that is brittle is basically not stretchable. It is hard, but it is brittle, meaning that it can crack easily. Can crack easily. So it's not stretchable that much, but it can sustain a lot of force. Can sustain a lot of stress. How? Look at this value. Look at this stress value for this brittle material. On the other hand, when you have ductile material, a ductile material, let's write it over here, is very stretchable. That's the meaning of being a nice ductile material, that you can make long wires out of it because it's so stretchable. You can make very thin long wires out of it. It's not hard because for you to be able to make wires out of it, it has to be not hard, and therefore it is ductile. And then it cannot crack easily, but because of that it cannot sustain a lot of stress. What you'll notice here is that this is their failure point for ductile materials, which is so far ahead of the failure point of brittle material, which is right over here. So for brittle material, they crack or they fail at so early, fail for brittle, right? And this is the point which is the fail for ductile. So this sort of tells you how ductile versus brittle is related to different materials, and how some materials are ductile and some materials are brittle in nature. Another curve that will help you get a deeper understanding of the atomistic phenomena happening in stress strain diagram. Let's look at it step by step for some sort of a metal, right? So you have again a stress strain diagram. You have this linear elasticity region. You have this elastic plus plastic region. You have this plastic region in which you have work hardening. You have necking, and then you have rupture or fracture. So again, the common points still remain the same. A bit weird difference you have than general curves that we are drawing till now is this region, the yield region. You have an upper yield point, you have a lower yield point, and then you have a plateau. So what is happening in the elastic region? Why materials are elastic? Because all that is happening is your bonds are just stretching. So for elastic, bonds stretch. So when bonds are stretching, they can come back and forth. They can stretch out and then they can stretch in. Because you're not breaking any bonds, when you release the material, it will follow the exact same path that it took, and it'll come back to its original shape because the bonds are just stretching. Right at this yield point, the upper yield point, what starts happening is that your atom starts slipping, and the bonds that were established over here start breaking. So this was, let's redraw this. This was connected here. these bonds are connected like this, and now you can see how the bonds have elongated or broken apart. And that's where plastic deformation comes into place. There is still some elastic these, so for example, these bonds are still stretching, right? So there's elastic plus plastic deformation happening at the same time. And then after this yield happens completely, when all the elastic deformation has stopped and it's only plastic, only slipping has happened, what this slip causes this is that at this slip plane where your atoms, so for example in this diagram, this will be your slip plane. This is your slip plane. At this slip plane you have dislocations piling up. What are dislocations? In a very simple sense, dislocations are sort of anomalies in your structure. These are defects of sorts. And what they do is that they prevent your. So let's write that here. What is happening? Dislocations piling prevent crack propagation, meaning that in this region of work hardening, even though you are deforming your material plastically, so you had plastic deformation, your material is permanently deforming. Because of these dislocations formation, your material is getting stronger. So work hardening, therefore stronger material becomes stronger, and that's why it's called work hardening, or it is also referred as strain hardening, because due to increased strain in this material you are making it harder, you're making it stronger of sorts. And again, what's the root cause? The root cause is the dislocation pile up. Always remember this, very important. The dislocation pile up is what is causing work hardening or strain hardening. But at certain point you will hit this location, which is this point over here marked in blue, which if you remember again is the ultimate tensile stress or ultimate tensile strength, after which necking takes over. There are no more dislocations to pile up. The energy that is required has exceeded. And what that means is that necking takes prominence over dislocation pile up. And then you could say that crack starts of sort. So this phenomena over here is sort of the necking, which is, so this is necking. And that starts happening. And once necking is happening, your material is getting weaker. So material getting weaker, because again there's a defect, there's a crack in the material, there's like a physical issue with the material at this point. It's sort of not usable anymore. It's like tearing a paper apart. Even with a small tear, with a small crack, that small crack could result in a very massive colossal damage to your paper. Now take that paper picture and think about a bridge. A bridge can have necking in its material. Once necking starts, you have big issues with that crack propagating. And at some point, once all those necking and cracks propagate and you have a lot of necking, your strength in the material is decreasing. That's why this curve goes down. All right. And you come to a point where fracture happens, where rupture happens. And this is sort of this example, your material fractures. Right? So this picture shows a very nice fundamental view of what is happening when you start elongating your material in different stages. Elastic stage, elastic plus plastic, all plastic, in which first you have work hardening, then you have necking, and then at the end you have rupture. So again, please try to read more about this whole principle about what is happening. Right? Let's try to see if we can do an example or two on this phenomena. So this example says you have a cylindrical metal specimen. The original diameter, or D naught, is given to you as 12.8 millimeters. The gauge length, the initial gauge length is 50.80. So length naught equals to 50.8 millimeters. And then this, it is pulled under tension until fracture occurs. So again, fracture occurs means that it is at this very end. And after that, so at the moment of at the diameter at the point of fracture, the diameter is 8.13. So the D sort of final is 8.13 millimeters. You'll notice how this has reduced, right? Your diameter has reduced. But another thing that you'll notice that your length has increased. Your fracture length, or the length at the point of fracture, is now 74.17 millimeters. They're asking you to calculate ductility in terms of percent reduction in the area and percent elongation. And they give you the two formulas. So you could just put in the two values, or you could just put in all the values that are given to you. Here, A naught, just to be clear, A naught will be pi D naught square by 4, and your AF will be pi DF square by 4. Keep the units in check. Because it's all millimeters and it's a percent ratio, you can keep everything in the units that are given to you. So you don't have to convert it to meters, because they'll all cancel out because it's a ratio, it's a percent elongation. And again, LF, 74.7, L naught, 50.8. Similarly, A naught is given by pi D naught square by 4. D naught is 12.8 millimeter. And AF is pi DF squared over 4, where DF is given to you as 8.13. So if you do the math, you can get some values, and I leave that to you to practice at home. And yeah, so let's try to conclude this by again drawing the same or similar curve, and let's see if we can do the labeling of this stress strain curve. So if I give you this stress strain diagram, we have to label the Young's modulus, the proportionality limit, the yield stress, the tensile stress, the fracture stress, the ductility, the resilience, and the toughness. All right, so let's start doing that. A very important thing that you could note here that I didn't mention earlier is this 0.002 value. You take the slope of this straight linear line that we had, and then you draw it out this with the same slope from 0.002 percent elongation or epsilon, and where it meets, this is how you can get your yield stress. So all right, let's do the markings in our plot. So the first very important thing we know is let's start with the Young's modulus. We know that the slope here, this slope, sigma over epsilon, all right, this slope is given as A. So I'm gonna just color it with pink. So I'll just write pink over here, which is sigma over epsilon, right, in the elastic region. Proportionality limit is this point where this line stops. So let's draw it with maybe a yellow color. So I'll write this as B, or maybe a red color. B. This is the proportionality limit. Now, using what I just told, that you take the slope, the Young's modulus, and draw a line out from 0.002 and see where it meets the curve. This, by green, is the point C, or the yield stress. So this over here is the yield stress. Oops. This over here is the proportionality limit. This over here is the epsilon. I mean, not the area, but the slope. Just to be 100% clear, I'm referring to the slope here. And then following that, you have the point D over here, which is referred as the tensile stress, the TS or the UTS, which is over here. Then you have the fracture stress, which is at the end. So somewhere over here, fracture stress, FS. This is your point E. Now, ductility is the entire area under the curve till the point E. So let's draw it with the blue color. So this in no sorry till the point you have fracture. So with this fracture, this entire region is how you can define the ductility. And the way you do that is that you take the same slope as the epsilon as your Young's modulus, and draw a line that traces itself back from here. And again, remember, ductility is sort of a measure of length of sorts, or strain, or change in strain, length or strain. That's it's sort of the unit of ductility in some way. So you draw this out, and you will notice that this length over here, where it intersects the x-axis, this is F, or ductility. Ductility meaning that till this point you can extend your material, and this is how much ductile it will be, or this is the relative change it can at max sustain, right? And then you have the last two values, resilience and toughness. Toughness is the area under entire curve. So I'm going to mark it with the green color. So literally this entire area, oops, this entire area under the curve is your ductility. All right. Now with resilience, that is the area as shown here under, I'm going to use this for color. Let's use pink on this. So this pink area that I'm drawing, which is till the yield stress. Again, remember point C is the yield stress. The area under, the area under this entire area is your resilience. So this entire thing is G, or resilience. All right. And again, remember the toughness is the area under the entire thing till the fracture point, right? So this entire thing, and maybe this will help you. So this H over here, toughness. This is this entire area that like I'm trying to shade over here till your fracture point from the very beginning. All right. So this sort of summarizes your entire plot of the stress strain curve, the different important properties, the Young's modulus, proportional limit, yield stress, tensile stress, fracture stress, ductility, resilience, and toughness. Very important mechanical properties of a material. We saw how different materials, ceramic, metal, and polymer, can have different values and why their curves vary so much. You saw how ductile and brittle materials are different. And then we also saw how there is an elastic region followed by elastic plus plastic followed by only plastic. And then we also saw how material elongates, and after the ultimate tensile strength it starts to neck, and then you create a failure or a fracture at the end. We saw the fundamental principle of what is happening inside at the atomistic level throughout this entire stress strain curve. We did some problems to see the difference between the stress and strain. So we saw how you can have engineering stress, how you can have true stress, engineering strain, and true strain. So this is what I want to cover in this lecture, and very important for mechanical engineers, industrial engineers, material science engineers. It sort of spans across different fields and is very important for different people. All right, thank you.